Okay, thanks, Matt. I've given this the subtitle of An Alternative History of Quantum Trajectories. It's not intended to be revisionist. To a certain extent, what you have is a sort of convergent evolution where different species with different DNAs come out looking somehow very similar, uncannily similar. And quantum filtering or quantum trajectories or stochastic master equations or quantum state diffusion, there's a whole array of different things which are mathematically very, very similar, but where their origins have been completely different. So many people from the physics community will be familiar with the quantum trajectories approach, which typically starts at the master equation and works away from that. What I'm going to do is to give the other derivation, which has come largely through the engineering community, which has a completely different set of objectives in what it's trying to do. Maybe make some connections along the way, but in many ways the thinking is almost the reverse of what's been going on in the physics community. So first of all, the term filtering confuses a lot of people because engineers use the word filter for a lot of different things. A filter, by and large, is a black box. You put some signal in and get a different signal coming out. As the name sort of suggests, you can use a filter to get rid of unwanted component of a signal, particular noise. So what's filtering? Basic problem we're trying to solve is how do we get the best estimate of a system based on either inaccurate or noisy information, or both in practice in general. And the term originally came from work of Gough and Wiener, who developed a theory of filtering out the noisy component of signals using a mechanical device often, or an electronic device, which really was a filter. What they did was restricted to stationary processes. So you typically found that most of the noise had a particular frequency and you got rid of that particular range of frequencies. So there was a lot of Fourier analysis in this. Engineers had to learn quite a bit of this. But it was restricted to stationary processes. So I'm going to go through the classical engineering viewpoint here, first of all. The great breakthrough in this came roughly at the start of the 1960s. In America, you had Rudolf Kalman, who came up with a filter, again using the word filter for some estimation problem where you're trying to get rid of unwanted, inaccurate information and filter it out in that sense. This was a major advance on what Wiener and Gough had done because it applied to non-stationary problems. In particular, it applied to dynamically changing systems. It was restricted to linear dynamical systems, but even still, this is a major advance. And it started to find applications fairly rapidly. It just because you're basically dealing with a mechanical or an electric system and you're trying to estimate the state, given noisy information, this is just about every inertial guidance problem. Another early example was fault-tolerant gyro systems for aeroplanes. You need 3 gyros to work out the X, Y, and Z. You can make it fault-tolerant by having 6 of these, right? And what the Kalman filter is just looks for the discrepancies between each. And I guess the big showcase was the radar system for the moon landings, right? In fact, they tested the system the day before they put Collins, Armstrong, and Aldrin up into space. Right? That was the first time they showed that the Kalman filter, which I think was a 21-state filter, actually worked with the radar system. Right? So that's how they landed the men on the moon. So I'll spend a little bit of time on the Kalman filter just because of its general importance. The aim, very simply, is you're given information, and we'll assume that the problem's in discrete time. There's a continuous time version of this, which I'll tell you later. But for the moment, we'll take discrete time. We've got observations, y1, y2, y3, etc., at discrete instants of time. And what we want to do is to come up with the optimal estimate of the state, or any function of the state, based on the observations we've made up to that point. Right? To explain what's going on, the blue symbol here, x hat k, is the optimal estimate of the state at time k, given the observations up to and including that particular time. The funny E symbol here, that's an expectation, but it's a conditional expectation based on what you've measured up to that particular time. The red symbol here, the x with a tilde on it, x tilde k, is our optimal estimate for the state at time k, given the information up to, but not including the most recent observation. So this is a prediction based on what we see up to time k minus 1 of what will occur. Now the whole issue of optimality here, what does it mean to have a best estimate, I'll come to later. The problem, why it's tractable, everything's going to work out to be a linear dynamics, and it's going to stay Gaussian, right? So we really need to know just the mean values and be able to track the variance, and that's enough to determine the state in the sense of a probability distribution on a state space. It's a recursive estimation scheme, because what you do is you take the information as it's coming in to update the state of knowledge of the system. So I'll just run through what's happening here. What you have is a model here. The model is a linear model. We'll assume, so how do you update the state? Well, it's based on the previous state. You can put in some input UK, so you are allowed to control it. But there'll also be some noise present, that's WK, which we'll assume to be mean zero Gaussian. So up here is what's actually going on in the real world. This dot might be your initial state. Then you're moving around based on this formula here, but it's random because there's noise entering into the dynamics. So where you are at, say, time k minus 1 will be random. The problem is you don't have access to this. Typically, you can't see the state. All you have are some observations which are determined by the value of the state at each time, right? So you get a sequence of observations in time. And effectively, all you know about what's happening is what you read out here, okay? So you'd like to know what's going on up here, but all you have access to, and it's typically partial observations, is the readout here, okay? The observations, again, we're assuming it's linear. The observations at time k depends on the state at time k. There's some, in general, matrix H. These can be vectorized. And we're also allowing observation noise to enter. So Vk here is an independent, we'll take to be standard normal variable. So there's noise in the dynamics, there's additional noise in the observations. Okay. So the reality is we only have access to the readout, and what we want to do is, based on the readout, come up with an optimal guess as to what's going on here. So I've drawn it in blue, right? That was the symbol for the Kalman. Yeah?
What were the conditions on the noise? And are they restrictive?
Hmm?
Are they?
They're independent.
They're independent, but okay, so
the means at 0, actually this has some standard deviation Q. We're taking the observations to be standardized. I've done it all as if it's just one variable. You can turn these into vectors if you want. In particular, H needn't have full rank, so you're only getting partial information. You can't necessarily recover exactly what your state is from just knowing Y. You can make these correlated noises if you wanted. That's all done. Yeah. But just for simplicity, I'm looking at the simplest possible case. So the question is, how do we get this part up here, which is telling us what we think is most likely to happen, optimal in some sense, right? Well, it's a recursive scheme, so what I have to tell you is how do you go from the last blue dot to the next blue dot, right? So the way it works is as follows. If we have our best estimate at time k minus 1, and let's say we've already computed its variance, we're going to come up with the best estimate for what it'll be one step into the future, but based on the information we already have. So this is a prediction. And there's a prediction step which is basically the following formula. It's a linear formula where you just take the dynamical equations, ignore the noise, and just say, well, on average, this is what would happen, right? So it's just the deterministic part of the evolution, ignoring the noise because we don't know what's going to happen. We'd say, on average, if you were here, you'd end up here at this red dot. So that's your predicted state. And you also work out the predicted variance from Kalman's rule. So now you say, well, if that's where we're going to be, that's our best guess for where we're going to be, what would we then predict to be the next measurement readout, right? And that's just, again, taking the formula for the observations, putting in our predicted state to say what the predicted measurement should be. We haven't added any noise in here because we can't predict what the noise is going to be, right? So this is just what we say on average we'd expect the next observation to be based on what we think on average the state should be in one instant time. So what we're doing is, based on the information we have up to present, predicting what's going to come in as the next observation, and then, as is essential in engineering, you're correcting. This is the whole idea of feedback. You make corrective steps based on what's actually happening. So you wait for the next observation to come in, right? Let's suppose it's up here. You look at the residual error. This is how far your prediction of what was going to read out is from what actually occurs. This is also known as the innovations. If the innovations was 0, would basically mean you got what you expected and you wouldn't do anything. If it's not 0, you have to make a correction, right? It tells you, well, how much your guess was out. So based on the size of this residual error, what you do is you apply a correction for your prediction, right? And the rule is you take what you've predicted and you make the following correction based on the innovations. And again, it's nice and linear. You also get for free the variance. And that's the recursive step. We've now worked out what the next one will be. And what we needed was to bring in the next observation. So there's a prediction step, then you measure, and then you correct for it. So that's the Kalman filter in a nutshell. So in all its details, this is usually the way it's presented. Prediction step, update step. So basically going from here to here, it's a 2-step. You go first to the prediction, then from the prediction, looking at what actually comes in, the correction based on the measurement update. So you combine it as 1 step, to go from your optimal estimate for the state at time k to the next instant of time based on the observation you have up to each time. Okay? And a crucial role in this is played on the innovations. The innovations is the difference between what you measure and what you would have expected to measure based on what you've seen up to that time, right? So it's the difference between your observations and your expectations. Okay. So I better say something about what it means to be optimal. Why is this the best thing you can do? Well, this goes back a long time in the history of mathematics, probably to Gauss, if not earlier. It's the least squares. It's the simplest thing to work with. So what we want to do, just as a general problem in probability, is given a random variable x, a set of observations y. For the mathematically sophisticated, that's a sigma algebra. So it's basically all the information about what we can measure, the observed, well, random variables we can measure. So we restrict to second order random variables, ones with finite second moment. The least squares definition here for best estimate, it's the random variable, which is y measurable, so determined by the information in what we're observing, such that this difference here, the error between our estimate and x, its second moment, which is basically the mean square error, is minimized compared to choosing any other z that's y measurable, right? Now, there's a lovely bit of geometry here because the second order random variables should form a Hilbert space, right? And the norm is just the root mean square. You've also got an inner product, which is just taking two random variables, multiplying them together and averaging them, right? It's a real Hilbert space principle. So then you say, well, let's restrict to only those random variables which are y measurable. Well, this is a Hilbert subspace, okay? Which we'll draw as a plane down here. So the question of optimality is, we have to find some vector in this plane here such that its distance up to original x, which typically isn't in this plane, is minimized. And the shortest distance, because we've geometry here, the shortest distance is just to project down, right? In which case the error is perpendicular to the plane.
John, sorry, I know you were very clear about this before, but can you tell me again what is the, so the tilde one is the one you predict based on, setting the...
There's no tildes in this.
Yeah, I know. And then what's the difference between the hat and the x without anything?
No, the hat
Can you tell me what
is just the definition. The hat, right, we start off with a vector x. X hat is the vector in this plane here, which has the least distance to x.
Yeah, but operationally in the process, can you remind me of what like the things are?
Oh no, this is for just general random variables.
Okay, but
Right.
what you call hat is what? Is that? Just redefine
It's an estimate.
Okay, it's your estimate.
Yeah. Yeah. So we want to find a random variable. The variables are now described by vectors,
Yeah.
right? So of all the vectors you could have, all the points in this plane, which one is closest to this x here in length? And the minimum distance has to be the orthogonal projection.
Okay, so my problem then is, I had the impression that the filter, the thing it does is that it kills the noise. Is it?
There's no noise. We're not talking about noise. We're just talking about a random variable and some information out of all the random variables we can construct using the information at hand. They form a plane. of all the things here, in the plane is what we can actually estimate. They're the random variables we can construct using the information.
Okay, so nothing depends on the knowledge about the model. Everything, all the observations of what you saw, a series of dots.
Know what maybe I'll come to an example in a moment. It's probably the simplest. So our optimal estimate, right, is just the orthogonal projection of x into this plane, right? And for the optimal estimate, the error, so this vector here, the shortest possible we can have from x into the plane, it's orthogonal to the plane. So we have this condition that the error multiplied by any vector y, so any random variable that's y measurable, that will have average 0. Okay? So maybe this will clarify what's going on. Suppose a random variable, we have a single random variable which is a measurement, right? Let's call it capital Y. And Corley Y is just a sigma algebra generated by that. It's just a set of events generated by this. And let's suppose for simplicity, the random variable is discrete, and it can only take on a certain finite number of values, n values. Okay? So what we would do is to say, well, let's introduce some functions that are just the characteristic functions for each of these events. So y takes a particular value, yk, and we take a random variable which is 1 if that event occurs, and 0 otherwise. Right? These are all projections, right? And because these events here are mutually exclusive, collectively exhaustive, it sums to 1. And it looks like a resolution of identity, but don't be too fooled by that, okay? For simplicity, we'll also assume that each of these events has a finite probability to occur. Now, what we're saying for another random variable to be y measurable, right? So what does it mean to be in this blue plane, which I showed earlier? Basically, it has to be of the following type. It has to be measurable with respect to the events described up here for the different k's. So on each of these sets where y takes a specific value, your random variable has to be constant. So basically, it's coarse-grained with respect to the information available in y. So we're seeking a minimizer out of variables of the following type, right? So here you can exactly compute the error, right? What we've got to play around with are the coefficients zk. So either by completing the square or differentiating with respect to the zk, you find out what the optimal values are that minimize this. And if you plug it in, these are what the optimal values of the coefficients are. You can write this a bit more suggestively as the inner product, right? The pKs aren't normalized. In fact, the norm is the square root of the probability to occur. But you see this has the form of a projection, right? There's another measure-theoretic interpretation for the optimizer, and this is as conditional expectation. You define the conditional expectation of, say, second-order variable x onto the information available, so that'll be some sigma algebra, generally y. It's the unique random variable that's coarse-grained on the information y, so it's y measurable, such that the following identity holds for any other variable y that's measurable with respect to the information you have at hand, okay? But this actually is just the projection again. So the conditional expectation is really just the orthogonal projection we've seen earlier. And there are a number of fairly obvious properties. By definition, the conditional expectation is y measurable. If we coarse grain a second time, we don't lose any more information, so we just get the original coarse graining. This last one, which says if we average our conditional expectation, we just get the average of x. That's what you'd get if you just stuck y to be the identity in there, right? So, yeah, one of the age-old questions that arose in engineering is if we can put a man on the moon, why can't we find a nonlinear filter, right? So, around about the time Kalman was working on this, a number of people were working on a more sophisticated theory, most notably Stratonovich. So we'll go into continuous time. We'll have nonlinear dynamics here. So V is a nonlinear function. In general, we have volatility sigma. W is going to be the noise. It'll be a Wiener process. Our observations, well, we've got some other nonlinear function h, which gives the information, plus more noise, another Wiener process. Again, you can take these noises correlated, but for simplicity, we'll assume that they're uncorrelated. And if you're taking any function of the state variable x, because this is a diffusion, this will also satisfy the diffusion equation, which looks as follows. There's a generator here, and the generator, that's the dt coefficient, is a second order differential operator of the following type. Okay? So, again, you ask the same sort of question. Given any function, right, and you want that function of the state at time t, what's the optimal estimate given your observations up to that time? And there's this beautiful equation. It's beautiful because I've taken the noise and the observations to be uncorrelated and had it all one-dimensional, right? But this is the result. This is the stochastic differential equation due to Stratonovich and also someone called Howard Kushner. And it's beautiful. I'm going to tell you why it's beautiful. Right? It comes in two parts. There's a dt part, a deterministic part, which is dynamical. Right? There's the generator. So it's the generator and f evaluated at time t in the state. And then you have the hat, which is a conditional expectation. Right? There's another term, which is information theoretic. Okay, the bit in curly brackets, it's a conditional expectation of a product minus the product of the conditional expectations. So you could call it a conditional covariance, I guess, right? And what's involved? Well, it's the function f we want to estimate, and it's the function h associated with the observations. So that's clearly something to do with information. There's, oh, what's happened? I pressed something. There's
Waking up? No.
I just pressed something. There's another increment here, di. What's that? Well, that's the innovations process. And this is the continuous version of what we'd seen in the Kalman filter. It's defined as, just down here, dy. So that's the increment in what we're observing, minus h hat dt. Remember, h hat is what we'd expect to get, conditioned on what we've seen up to that time. So this is our expectations. So again, it's our observations minus our expectations in infinitesimal format now. This is the time continuous version of the innovation. So this is a stochastic process. And for this type of problem, and this is where it starts getting hard analytically, what you have to show is that the innovations process is statistically regular. In fact, it should work out to be a Wiener process again, right? Yeah?
If I look at the structure of the expression, going back to the second line,
This
Is
line?
it exactly dVt?
Hmm?
What you call DIT, isn't it exactly dVt? Just
No, this is part of the model. This is the noise in the observation. Yeah, there's a hat here. I should also mention, just very quickly, this is sort of going from Schrödinger to Heisenberg or back. Rather than working with the conditional expectation for a function, you can say, well, is there some sort of density I could use instead? This would actually be a stochastic process whose values are probability densities. So we can rewrite the Kushner-Stratonovich equation, if such a thing exists, in density format. And it's nonlinear in rho on this side because we have this here, which is the expectations coming from the innovations. So we have a rho squared here. So that makes it mathematically hard, right? I should also mention that if you averaged over the innovations, so basically say we don't care what we're actually measuring, if you average then over this density, you recover a Fokker-Planck equation, right? L prime here is just the joule of the generator, this second order operator, right?
I need to apologize because I lost track of prime as differentiation. Differentiation with respect to.
Yeah. Oh, I'm only in one degree of freedom here, so this prime is, should have used a star or something. We had the same problem yesterday. But then you end up with C-dagger algebras and so on. Yeah, and I'll just briefly mention, for leaving the classical world, there is another way of looking at this, which was later discovered by Moshe Zakai, that you can actually come up with a linear equation for a density. Problem is it's not normalized, but it's linear. So if you're going to sacrifice the normalization, you get this nice equation here, such that if you do normalize it, you end up with the density for the Kushner-Stratonovich equation. So you can check using the Ito calculus that if you have this, then this thing here satisfies Kushner-Stratonovich. Okay? Right, I'll just briefly run through the Kalman-Bucy filter. So this is where you do the Stratonovich filter with everything linear and Gaussian, right? Linear quadratic Gaussian. You get an equation like this for the estimate of the state, but because of the covariance, you have to estimate x squared, right? How do you get x squared? Well, you have to estimate x cubed. Runaway course of dimensionality, as it's known. But I said this is linear quadratic Gaussian, something has to give. It turns out that if things are Gaussian, the higher order moments can be worked out in terms of the mean and the variance. These are conditional objects, and if you substitute this in, you actually find the following equation for the estimate x hat, and for the conditional covariance, you actually get a deterministic equation. It's a Riccati equation. Okay, this is well known. I'm not going to dwell on this much more. Right, so quantum filtering. Right, so question is, what's the difference between macroscopic objects like a spaceship landing on the moon? Slava Bilavkin used to say we should be using filtering theory to, an example would be electrons moving in a bubble chamber, right? So how do we go from macroscopic to the quantum world, right? As you know, Matt and myself are writing a book. This might be our title, right? So it's all filtering, but it's filtering with quantum mechanics, right? So can you actually do it? Yeah, we're going to hear from Pierre Rouchon a bit later. This is this famous experiment they've done in Paris where they're trying to control a cavity mode, put it into some non-classical state, and what they're doing is passing Rydberg atoms one by one through the cavity. And as the Rydberg atoms come out, they make a measurement on this. They learn something about what's going on in the cavity, and then they can use that information. It might be spin up, spin down, because it's really a two-level system they're interested in. Based on that information, they have some correction to restore the cavity back into the desired mode. So I guess Pierre will be talking about this in some detail. So let's suppose that really it is a qubit model, and we prepare this in the down state, and cavity mode is in some well-defined state of psi, right? And initially they're independent before they interact. So it's just the tensor product of the two gives the state. So that's before the atom goes through, interacts with the system, so we apply some unitary operator U, and afterwards we can then measure the atom to see if it's spin up or spin down. Right? And we get a bit of information from this. And I'm going to assume that the time of flight through tau is very small, and I'm going to assume that the unitary looks something like this. There's a bit h, which you'd say, that's a Hamiltonian, which it is. So that's really the dynamics of the cavity. But then sigma plus and sigma minus are raising and lowering for the two-level atom, right? And we've got an L and L star, which is what happens as back action to the system, right? And to first order, throwing out the bits that aren't going to contribute, this is what it looks like. So we've root tau terms here. There's a tau term here, and beyond that we can forget. And you notice there's already an L dagger L term here, which sort of looks a bit like damping, which indeed it is when you average out. So what we're going to measure is not spin up or spin down, it's actually the sigma z, if originally things were aligned in the z direction, okay? So you do a measurement and you're just going to get one of two possible eigenvalues, plus or minus, right? And you can work out from quantum mechanics what the probabilities are. It's probability 1/2, as it should be, plus or minus some small correction which comes from the fact that the atom has interacted with your cavity, right? That would be root tau. And what happens, and this is just a von Neumann projection postulate, once you've measured the two-level atom, you get a collapse of the wave function, right? Which basically means that your state for the system changes to phi plus or phi minus, so eta is the plus or minus here, which just takes the following form. So that's dependent on whether you measure, you collapse into this state or this state here for the two-level atom. Okay, so you can then consider the continuum limit of this, where you take tau going to 0. So basically take it to be an infinitesimal dt. Roughly speaking, root tau eta, these bits you can think of as the observation increment and the limit. And you get a sort of central limit effect. So our equation for what's happening, this is for repeated atoms going through faster and faster so that it looks like a continuum, is an equation of the following type here. So that's just the last equation souped up into continuous. And I'll just go back. Here I had a proportional to because I wasn't worried about normalization. This thing here, I'm not going to call it psi anymore because it's not normalized. I'll give it another name. But this is actually a Zakai equation. Because if I now normalize it and just use the Ito calculus, I get the following equation. This is a stochastic Schrodinger equation. This has reoccurred in a lot of guises, quantum state diffusion, work by Guessin, by D'Arcy. Quite often the noise here, which is a Brownian motion or Wiener process, is just put in there as something that somehow appears by magic, right? But in our case, the noise is actually the innovations. It has a very clear, specific physical interpretation, and it's information theoretic. It's coming, by and large, from engineering. The lambda in this is actually the estimate of L plus L star, so you can think of this as a quantum measurement of L plus L star, that particular observable of your cavity, right? And here's the remarkable bit. You can say, well, can we actually write down the filtering equations? So basically, if this is your Schrodinger picture, what's the Heisenberg picture? What happens to the observables? You get this beautiful equation and compare it to the Kushner-Stratonovich, right? There's a dynamical part, and the generator here is actually the Lindblad generator. You've got the innovations, and the information theoretic part, again, it's a type of covariance, but now quantum covariance, because the X's and the L's and the L stars don't commute. Okay? But you can see how this looks like the Kushner-Stratonovich equation, at least in principle. And just working backwards, we can say, well, couldn't we get this conditional expectation of an observable X by just having some random density matrix rho? You can. So this is the equation it'll satisfy. It's a nonlinear equation. That's your stochastic master equation. And then finally, you can just average out your observations, so it's non-selective, and you're back down to the master equation. So physicists usually work in reverse. They start from the master equation and then try and deduce all of this backwards, right? But as far as we're concerned, the master equation is a derived object from the theory. It's the endpoint rather than the beginning. Okay. Now, I'll tell you a little bit about quantum probability. Quantum probability is the generalization of classical probability where you go from random variables to generally operators. And to get the topology right, you usually look at a von Neumann algebra. And the probabilities are determined typically by density matrices, so expectations occur as follows. It turns out if you take the state to be normal, when we say normal state, we don't mean Gaussian, we just mean normal in the sense of a continuity. But it basically tells us that we're safe to work with the usual density matrices. So commutative examples of this are just a classical probability where your algebra is just the bounded functions on your probability space, and your expectation is just with respect to probability measure. So that's all classical. And really what you're doing is you're averaging over some sample space, right? Quantum mechanically, it's different. You're taking trace of an observable self-adjoint operator with respect to some density matrix rho. Okay, so an observable, I hope you all know what this is. It's basically a self-adjoint operator in your algebra. Usually we think of some concrete example where there's an underlying Hilbert space. And observables can always be determined by their spectral measure. So this is a projection value measure pi, right? So for any function of the observable, we just integrate that function with respect to the spectral measure. And if we want the probability distribution of the observable in this particular state, E, that's what it is. That's the spectral measure. We just take the spectral measure and average it with respect to the state rho. So if you're a quantum probabilist, an observable you'd actually say is a completely positive embedding, J, of a commutative space, say these functions here, into some algebra. And how it works is you take your function f here, some bounded function, and you come up with this here defining an operator. So it's a quantization. Embedding also means that it's homomorphism. So if you have f times g, that gets embedded or mapped to the function f times g goes to the operator f of x times g of x, but they commute, right? So no problem there. You can actually generalize this as saying it's a CP embedding from a non-commutative subspace B into some subspace of A, right? We don't actually need this. So roughly speaking, a quantum random variable you can think of as a CP map taking you from some algebra here into some algebra here, let's call it Y, which is contained in a larger probability space. Okay, now the real key question is whether quantum conditional expectations exist, right? So what would be quantum conditional expectation? We have some algebra of operators A, that's the big square here. So this is everything we could have in the model. So all observables relevant to the problem. And then we want to pick out some subset, so some von Neumann algebra of the operators we actually we're interested in as a subalgebra, so some subcomponent. And the difficulty in quantum mechanics, don't be fooled by this looking like a Venn diagram. The problem is when I say here's a subcomponent of the quantum world, what do you actually mean by what's outside, right? We're talking about operators here. So basically what we want is to have some way of saying we have an observable up here, or some operator x up here. How do we project down into this subspace? How do we coarse grain on this smaller algebra here? Okay? So basically it's a conditional expectation is one of these CP maps from a von Neumann algebra into a subalgebra, which is also a projection, right? If you project down once and then you try and project down twice, it doesn't change anything. One way of getting it is to look at our definition of quantum random variable and saying, well, let's suppose this subspace Y came from a quantum random variable. What are the conditions on the quantum random variable for it to lead to a conditional expectation? And one of the definitions is conditionable. And this is very old stuff, goes back to Takasaki in the 50s. Basically what you want is a map from your big algebra into this space here, let's call it G, such that it's going from this to the embedded one. G will be the local inverse of J, right? So you go from here down to here, over to here. So the composition of G and J would give you a conditional expectation. And the good news is that when you have this, everything works, right? You get this nice property here, and on the strength of that, you actually get the least squares property as well. So it's least squares in this sense. The bad news, of course, is that this doesn't always work. It's the case that a quantum random variable is conditionable if and only if the following modular invariance of your algebra Y holds, and I'm not going to go into that because I don't know this story. I think Hadis Amini, when she comes here, is going to talk about this problem, filtering with these non-commutative problems. So we're going to consider something a little bit less ambitious, but more physically reasonable. We're going to, first of all, pick our model of interest. So this is the whole quantum world we want to describe in the model. That's algebra A with an expectation E. And then we're going to say, well, what are we going to try and measure? The measurement algebra Y that we want to measure is going to consist of commuting observables. And the reason for doing that is, yeah, we could try and measure non-commuting observables, but as soon as you measure one, then you go and measure another one. If it doesn't commute, you invalidate what you've already measured. If you go back and try and measure it, you're not guaranteed to get the same result. So this is the non-demolition principle. And basically, it's an excuse to say we're only going to consider measurements where all the observables we measure commute with each other, right, throughout the entire experiment. Now, given that, what can we estimate? Well, if you want to estimate anything else, the logic is that it has to be something that if you did include it in the measurement, it would still be non-demolition, which means it has to commute with all the observables you're measuring. So the only things we're going to try and estimate, we're not going to estimate everything, the only thing we're going to try and estimate are those operators which commute with everything that we intend to measure. So the set of all things that commute with everything we want to measure, that's the y, this is called the commutant of y, and that's y prime. Sorry, another prime. But, so this is the picture. We have a commutative algebra, that's the red blob. We have its commutant, which is the green blob. Everything outside we don't bother with. We're not going to try and estimate anything that doesn't commute with our observations. And what you can show is that there now always exists a conditional expectation from the commutant into the measurement algebra. I'll just get rid of the rest of the world to explain this. You have your x up here, and the thing about the x is, because it's in the commutant, the x and all of this and the red blob all commute with each other. And once things commute, they're classical. And conditional expectations always exist classically, so there is a unique element down here, which is the classical conditional expectation. So it's actually trivial up to the point. I'll just go back. If I chose any other element of the commutant, I could likewise project down, and that's uniquely defined, unique up to almost ever. Okay. But the thing is, an element over here doesn't necessarily commute with this, because the commutant itself doesn't necessarily have to be a commutative algebra, right? So this green blob here is genuinely, may well be genuinely quantum. It's non-commutative. Okay. So for open quantum systems, just to run through yesterday's, 5 more minutes. So this will be very quick. We've seen this yesterday, the unitary, but just emission absorption. So it's an open system. So this would be the continuum limit of what I've shown you earlier. The Heisenberg-Langevin equation looks like this. And again, the dynamical part is just a Lindblad generator. Again, if you average in the vacuum state, you can get the equivalent master equation. I just put that on to emphasize the master equation comes as a special case of this once you average things out. I also mentioned the scattering process. So this is the most general form of a unitary, certainly for just one input. You can generalize it further for multiple field inputs. So we've seen a bit of this yesterday. This is what the Heisenberg-Langevin equations are. So this is basically a quantum mechanical system, an open system being driven by the external noises of the field. The other thing I didn't tell you about yesterday are the outputs, right? The outputs I got from the inputs, and you go into the interaction picture, you multiply by u and u star, and you get from the Ito calculus the following formula for the output fields. They're again canonical fields. Now, here's the filtering problem. What we want to do is to pick some self-commuting set of observables, so time dependent, so it's a commuting process. Typically we'll want it adapted. And then usually you go, because you're interested in the output, you apply u star and u either side. So what you end up with is a commuting set of observables adapted in time. And this is going to be a measurement algebra which is growing over time as t increases. This von Neumann algebra generated by these commuting set of operators that you're observing is growing all the time. So this is sometimes referred to as a filtration. It's essential that this is a commutative von Neumann algebra for each time t. what lies in the commutant, the good news is that if you take any observable of your system and move it to a time s, it'll lie in the commutant for times s greater than t. In other words, you're capable of estimating anything now, which is filtering, or anything in the future, which is prediction. You can't estimate things in the past, so there's really no smoothing in the traditional sense, because that's sort of retrodiction and you're trying to work quantum mechanics backwards. The general theory then of filtering for your observable at time t, based on the observations you've chosen to measure up to time t, that's the filter. I think this was done by Slava Belavkin, who you saw briefly there. Okay. Slava Belavkin derived just from this principle. There are a number of ways to get at these equations. These are the filter equations. For quadrature measurement, it's just the analog of Kushner-Stratinovich, right? So that's exactly the equation I derived by just passing to the continuum limit of Pierre's experiment with Rydberg atoms, okay? You can also count photons at the output, and this is what it looks like. So that's how engineers would think of it. If you're a physicist, you might say, well, what are the density matrices looking like? Well, you just pass from this, which is Heisenberg picture, to this, which is the Schrödinger picture. Right. I'll just make one or two comments very quickly. For the cavity mode, where everything's Gaussian, right? Your collapse operator is just the annihilation operator for the cavity, and we take the Hamiltonian just to be harmonic oscillator. You can walk through the filter, and you actually get a linear equation for the estimate of your cavity mode annihilator, involving a pair of functions which satisfy sort of a Riccati equation. So this is the Kalman-Busi filter for cavity modes. And I just wanted to stress that the A hat here is the estimate for the annihilator. It'll commute with the estimate for the creator, because they both live in this commutative subspace we're estimating on, because all our observations are commutative. And very quickly, I'll just show you this slide. With Matt James and Henry Norden, we've developed a theory of filtering recently where we try and go beyond the Gaussian input case. In particular, we were very anxious to say, well, can you do filtering for non-classical states? So our proposal was to put in another filter here in the engineering sense, so another model which takes in vacuum noise but pumps out something that's non-vacuum and non-Gaussian, so a single photon state or multiple photon state or a Schrödinger cat state or whatever, and then say, if this is passed through your system, your atom here, and then detected either by number or quadrature measurement, what you get. So for a single photon, we actually get a system of equations. Pi11 is the actual filter we want, but you have to solve a hierarchy of lower states. So this is a one particle, but you also have to solve a vacuum one lower down. So it is doable. We've also done it for the cat states, and more recently for continuous matrix product states as well. So I've got to wrap up that. Chairman's getting anxious, I think.
Time for a couple of questions before we finish up.
Okay. So something I've seen somewhat recently is the role that the
conditional density matrix, like teasing out physics, it's hard to see otherwise. And this is something that the few groups in Waterloo have actually been playing with, where they've been saying, well, we make this conditional measurement, we pick up a bit of phase information in our system, which through a weak but a rare but strong measurement leads to a conditional state that has a phase you normally couldn't measure. I'm kind of curious if this, I mean, formalism here encompasses that general concept, but I'm kind of curious how you can see the set of conditional states as being sort of fundamentally different from a state control perspective than what you might get with the other handles available to you.
Yeah, I'd be curious as well.
In other
So I
words,
can't give us
think of it as quantum control problem, right? I've got some
a realistic answer
some
to that.
terms that I have input, that I have some control over.
Yeah,
And now I have this new stuff. How does this add?
Jake, by and large, I've done this and avoided philosophy. I think some of these questions are more of a philosophical bent than a mathematical or engineering bent. I'd have to look at the work beforehand, but before making any comments. But by and large, myself and Matt stay away from philosophy.
Sounds like a good topic for the club.
No, it's
I don't want to dismiss the
Yeah,
question.
no.
It's just
it's not
I have a vague feeling that
it's a control
it's
question.
down to what you actually mean by a density matrix and getting into rather philosophical. So there's no way I'm going to be able to answer it in the next 5 minutes.
Can you understand from this formalism how you can improve the controllability of a system with feedback?
Yeah, I mean that's one of the goals. I mean
It's the same
that's
question.
the whole problem of control engineering, right? How do you now come up with some performance criterion and then seek
So as an
how do you
example,
engineer the
yesterday's
environment?
talk-
How do you choose which thing to measure, and so on, to optimize whatever performance criterion you're looking at? That's the whole goal of engineering.
Management theory was certainly this theory.
Well, I just think about yesterday's talk on the experimental side, where the point was that some preparation plus some Gaussian controls leads to a non-Gaussian output, right?
Yes.
That's an
Yeah.
improvement of control using the feedback. And I'm kind of curious how we can generalize that understanding.
Yeah, I mean, we were very interested. I think you're talking about Akira's talk.
Yeah.
Yeah. Particularly the nonlinear feed forward, which, because you're talking about measurement and it's a non-demolition measurement, you're basically saying we have this quantum model, but somewhere in the middle of it, there's a little bit of classicality. We're saying we're going to measure this and it's classical and we can use, not quite classical probability, but this extension where you can at least estimate what's going on in the commutant. So yeah, that's where you can start formulating control type problems. It sounds like a very interesting problem to work on in this workshop. Yeah, no, I fully agree. That's an excellent topic for the discussion. Yeah.
Okay, thank you very much.